Good afternoon. Hello. Good afternoon. Yes, kindly check on YouTube, Davy Manyika live streaming, if you are able to get that so that you can text others so that we start. Yeah. There was no connection. YouTube. So let's try. This is you. This is right?
Yeah.
Yes. Seems the person that given left it open.
I uploaded on my machinery to this system.
You can't see the one that is right? There is no way to share the link.
I think it was
I can repeat it. Yeah. Yes, okay. That's it. You are able to connect. It's working. You are able to get the sound. Are you able to get the sound? It's a bit low. Okay, let me just adjust it. Oh, okay, that's fine then. We can start. Okay, just forward the link to the group for everyone to join. Yeah. So I can't see myself. More than each other. More in front.
No, this one is some minutes behind. Wait for the story.
How many minutes?
That's what I like. The time you were there,
Let me see.
yeah. So this is what
What's this one?
that's it.
Okay, I think we are set. We can start. Just confirm by typing yes if you are able to get me so that we can start, please. Your camera? Okay. Push that button, close it. Okay, so like I mentioned in the morning, that we're supposed to start looking at work, energy, and power. I've already sent you the notes, and I've equally sent you the 3 tutorial sheets. I've equally sent you the 3 tutorial sheets. So the first tutorial sheet is actually looking at this that we are starting today. So the first thing we want to look at, we are saying that we are looking at work, energy, and power. So we are not going to look at them at once. We are going to look at them one after the other. So the first thing we want to look at is what is called work. So like I mentioned, this is not something that is too new. This is not too new to everyone, and I'm sure that at high school you also looked at work, energy, and power. So I want to just go straight and define what this work is. By definition, we know that work is nothing but force multiplied by the distance. That is the definition. So in other words, what we are saying is that this work is nothing but the change. So we are saying this is the change in the kinetic energy. As simple as that. So we have to if we are asked to say we define what work is, don't start giving stories. You can just write work is equal to force multiplied by distance. That answers the question, and you don't need to start writing stories. Okay? So, or in other ways, you can say work is nothing but the change in kinetic energy. So we move on. We know that here, this statement, we can actually write it in mathematical form as work is equal to the change in kinetic energy. As simple as that. So, in terms of definitions, we've defined what work is, and we know from our simple high school science that actually energy is just the ability to do work. Energy is the ability to do work. Work is the change in the kinetic energy, or the product between the force that is applied to a body multiplied by the distance that it covers. Energy is the ability to do work, and then power is defined as the rate at which work is done. That is how they are connected. So I'll repeat that. Work is nothing but the change in the kinetic energy, and energy is nothing but the ability to do work, and power is the rate at which work is actually done. As simple as that. So how do we define that in terms of the mathematics? All right. So we are saying that the power is nothing but work divided by the change in time. As simple as that. So we are saying that power is the rate at which work is done. Full stop. So don't start telling stories when you are asked to define these simple terms. Just go straight to the answer. All right, so we move on to what is called kinetic energy. So like I mentioned, in the first place I said that the change in the kinetic energy is what is defined as work. So in the same way, this kinetic energy all right, this kinetic energy, which we are calling K, is nothing but half mv squared, as simple as that. So this is how simple the physics is. You don't need to complicate it. Kinetic energy is nothing but half mv squared. So that means if the work is given by the change in the kinetic energy, it means that the work, which is the change in kinetic energy, must have the same units with the kinetic energy. As simple as that. So what we note is that this work and kinetic energy have the same units. Just need to note that. Right, so we move on. Okay, let's look at, of course, these units here, we all know that these are just nothing but the joules. I think that is straightforward. We don't even need to remind you at this level. Okay, let's look at a simple example here before we can continue. All right. So the simplest example that we can give is where you have, say, that is your rod where you are moving. Then you have this guy here who is pulling, say, a bag. This is you entering Mulungushi University, of course. We don't know if this is Matthews or whoever. So you are trying to pull this bag, which is actually moving on wheels. So let me... All right, guys. I was just trying to check on some of your comments so that I'm sure we are on the same page. So what I'm saying is that, let's say this is Matthews, and he's coming into Mulungushi University. So you are pulling a bag at a certain angle, which we are calling theta, and then you are moving a distance. Let's say this is A, and you are coming to B in that way. Then you have, this is your angle theta, which is between the ground and the angle at which you are lifting this bag. This is the amount of F that you are applying. So what does that mean? We know that from definition, we have said that work is nothing but F multiplied by D. But this now, from the first topic that you did in physics, you had looked at this is your X, this is your Y. In an event that you have an angle that is going in this direction, which is F there, this is your theta, it means that you were trying to resolve the F into X and Y components, where you were doing your tables in this manner, where you had your X and Y, then you were trying now to find the components and then you add them. I think I shouldn't go to that. You've already looked at it. So in this case, straight away from your, the physics that you've learned in the first lesson, it entails that from here, this F is not entirely F in totality, but it is not moving in this direction, but it is at a certain angle, which is making this angle theta there. That means this F now no longer, we cannot say F is equal to F, but now it has to be multiplied by the cosine of what? Of theta. In other words, this now becomes work is nothing but F, the cosine of theta, right? Then that is how you actually, you have this F, which is this, so that becomes that. Then we still have this D that we have to multiply, which is the distance from A to B. So in other words, what we are saying is that work now must be equal to, we have this distance, then we are multiplying it by F, then by the cosine of theta, as simple as that. So that is the first example. We move on. Okay. So I would encourage you to take some few notes as we are trying to, discuss. It's better you take few notes. They will help you when it comes to revision, because you will not be able to read all these notes in just a few minutes towards the exam. So it's important that you actually go through. All right, so we move on. Now, in an event that we have some free falling bodies, so remember we had said that work is nothing but the change in the kinetic energy. So we said work is nothing but change in kinetic energy. Now, let's imagine a situation where we have this body A and the ground is here. We have another body B in that situation. So we may call this our example 2 if you like. So the other body is falling down. The other one, we are trying to throw it up. As simple as that. So the meaning here is that we are trying to move these two bodies at a distance which we are calling h in that way. All right. And what does that mean? We know that by definition, this body which is here, there is some amount of weight that it is pushing on the ground. This is our ground, of course. And this we are saying that this F here must be nothing but the mg, which is the same as what you call the weight. All right. Now, at a certain point, at this point here, we have, if we are pushing this in that direction, it means that this body now is there's a certain amount of force that is being exerted on this body to make sure that it goes up to come to a certain height, which is what? Which is h. Okay, so if you are lifting this body from this point B to point A, the implication is that you have to do some work. And the work here we have said, it is nothing but the change in the kinetic energy. So we know that at this point, the work done now for you to lift that would mean that we have the F, we are multiplying this by the change in the y direction. Why am I saying in the y direction? It's because from here, you can easily, have your y and your x axis. If you look at this body, it is not moving in this direction. No, but it is going in this direction. So this is your y axis. That's why I've said the work done on this box must be the F multiplied by the change in y. How do we rewrite this in order for us to understand? This is as simple as the high school formula mgh, as simple as that. Where this is nothing but this F, and the height h is nothing but the change in the y direction, as simple as that. All right, so we continue. Okay, so in the same vein, we can look at the next example, which we are saying the work done by gravity. We know for sure if, say, you are holding something here, which is a body, right? And this is the ground. The moment you actually release this body here, it will actually fall down due to gravity. I think that one is straightforward. We don't need to explain what we mean by that. Okay, so now we want to see the work done by gravity on this body here. How do we define that? We know for sure that if a body, for example, this is a body, it's going down in this direction, it is going towards gravity. The mindset from the mathematics point of view is that when you have the x and y axis like that, we know that this is your positive, and in this direction you have your negative here. And here you have your positive, and here you have your what? Your negative, as simple as that. But in the case of gravity, when a body is actually going down, it means that it is going towards gravity, and that gives you a positive figure. When it is going in the opposite direction, which is up, it means that this now becomes negative. So make sure you don't confuse this with what you know from the simple mathematics. Don't confuse the gravity, and make sure that when the body is coming down, you don't forget to indicate that actually the work done is positive, and when it's going up, you indicate that the work done is actually in the negative direction. All right. Okay, let's look at a simple example in that vein. Okay? This is just a simple example to show us what we are trying to talk about. The first one, in terms of figures, we want to pick the one that we had started with. This is a box, and we are trying to pull it at a certain angle. Then here we have theta, where our F is nothing but 45.0 newtons. Then you know that at this point the velocity is 0. Then this is moving in this direction to come to this point, where now the V is equal to 2.60 meters per second. Okay. Now, we know that given that the work done is nothing but 50 joules. So now we have been tasked to find, so we are told to find theta. How do we do that? This is very simple, of course. We know that is our solution. We know the initial velocity is 0. The F we have been given. The theta is what we have been asked to find. Then we have the work that has been given, and we have the final velocity. So don't forget that we said that the work done is nothing but the change in the kinetic energy. We have the kinetic energy at point A, and we have the kinetic energy at point B. So the difference in the two is what gives us the work, which we have already been given in the question. So, but the question is asking us to find what? Theta, as simple as that. So how do we work out that? We know that this is the same as F, which is this F here. We are multiplying this F by the cosine of theta, which I mentioned in the earlier on example, to say since F is no longer in this direction, it means that we have to multiply it and get the component, the x component of F in this direction, which is nothing but F cosine theta. Right, so we have F cosine theta, then we multiply this by D. And this D, we know for sure, is just the distance from here to there. That is our D, the distance covered. So now, we have this, we have that, we have that. So this is what we don't have. And that is what we are trying to find. So we have to make this now the subject of the formula. So what do? We have theta straight away must be equal to the cosine inverse of work done divided by FD, as simple as that. This gives you nothing but the cosine inverse of 50 divided by 45 into, so we have 1.5 meters, which is a D. I didn't write it here. That is 1.5 meters. So you have 1.5 here. So that straight away gives you 42 degrees, as simple as that. All right, we move on. So I will introduce you to something small, but it's just for you to understand that actually this work can either be negative, it can either be 0, or it can be positive. Right. So let's look at what we are calling positive, negative, and 0 work. Okay, so like I mentioned, this work that we are talking about here can either be positive, it can either be negative, or it can be 0, depending on the scenario or the way the question has been phrased, this weight can change. So the first one that we want to look at is the positive scenario. In this event, we should have a situation where all these angle theta must be between 0 and 90 degrees. So this is our F, and then we have this, which is our D, of course. So in this scenario where we have the theta being between 0 degrees and 90 degrees, the implication here is that the theta must be less than 90 degrees, and that means the work done will be more than 0. In other words, it will be positive. So that's simple. In an event where we have negative, the implication is that this must be at exactly 90 degrees. If we have F in that direction, then we have D in this direction, of course. Then this is our 90 degrees, which is our theta there. We know for sure that the work done here must be, if we are saying that theta is equal to 90 degrees, what is the implication there? We know that the work done, in fact, this must be 0. Sorry for that. I've picked on the wrong diagram. This must be a 0 situation where we have a 90. So we know that this is 90. The work done here must be F cosine of theta. So we know that this cosine of 90 degrees gives you what? The cosine of 90 degrees gives you 0, actually. That's what makes now all this work to be equal to 0, as simple as that. Because the angle between the x and the y-axis is 90, what you see is that this f now will be multiplied by cosine of 90, which gives you 0. Now let's look at the negative one. In the negative situation, what we have is just the opposite of this. In other words, if this is negative, what we have is such kind of a situation. This is our theta, and then we have F here in that direction. Then we have D in this direction, so that the theta is actually greater than 90 degrees. We know for sure that the cosine of any angle, for example, you can pick 270 here, and you realize that you are going to get a negative number. And that means the work done must be less than 0. As simple as that. All right, we continue. Okay, let's look at another critical example. All right. And this other example is what is called an object dropped from rest. In other words, you have a block like this. That is your ground. Then of course, maybe this is another platform. Then you have this, which is your block, and it's coming down in this direction. So the implication here is that, and I want you to pay particular attention to the last formula that I'm going to put here, because this is a small formula that most of the students actually forget, especially in the exam. So you try to use the formula for work, the answer is not coming out. You try to use the formula for energy, the answer is not still coming out. You try to use, maybe you try to use the formula for power, still you are not getting the answer. It's because of this small formula that I'm going to put here. And please pay particular attention to it, because most students forget about it in the final exam. All right. What we are saying here is that we know for sure that we've defined work to be equal to mgh, as simple as that. Then we have also defined that this same work is the same as the change in the kinetic energy, which is nothing but half mv squared. This is for this object that we are dropping from rest position and it's coming down like that. So the velocity at which this block is moving, which is v, is defined as 2gh. This formula is very important. The velocity at which it is dropping is given by the square root of 2gh. For now, you just need to memorize this formula. As you advance, for some of you who are going to advance into the field of physics or any other higher level, you are going to know how this formula comes about. For now, look at it as it is and you can actually keep it. So this is the velocity at which this body is moving when it is dropping from that point coming to the ground. So it is given by the square root of 2 multiplied by gravity multiplied by the height. Please, in your notes, put a star here. Today I'm reminding you that you are going to forget about this. Until you forget about it, that's when you remember that I had mentioned that a lot of students, a good number of students, especially at first year level, they tend to forget this equation. So there are questions that you are going to find which will not demand any other equation apart from this. And if you fail to recall this, then you will not be able to produce the required result. All right. So we continue. Okay, so I just wanted to put it clear. This is in a case where this block is falling down, then you have that. So I'll give you just another scenario which you can still use that formula, the same formula, but this time around you're not using the height, but you're using the length. So these are questions where you look at an incline. For example, you have such a situation. If you have a body there and it is coming in that direction. Okay, so what do you have? You have this as your angle theta. Then, what else do we have here? We have our height, which is this h here. So we know for sure that from that definition, we have v being equal to 2gh, which is the square root. But this time around, this h, which is this height from here to there, it's not what is being covered. This is covering this distance from there to there. So now we have to look for a solution. In other words, we can put a capital H here because it's not the one that we are really looking for. So now, this is the L that we want. Okay. What do we do next? We know that the velocity for a free-falling body is given by 2gh. Now what we want is a situation where we are trying to calculate it from this direction because we know for sure that this is not the height that the body is going to cover. It's not the distance, in short. Because if we say this is point A, this is point B, this is point C, what I'm trying to say is that this body will not cover the distance AB, but it will cover the distance AC. So now we need to find the relationship between this AB and AC in order to replace the actual distance that the body will have to cover. Right. So in that case, you can use the simple formula from high school, F is equal to MA. I know this, we are familiar and we know about it. Okay, and we know that the velocity, and we know for sure that the velocity is nothing but AT, in other words. So we know that V is equal to AT. So what else don't we know? We know that L now will have to give us half, which is half AT squared. Then the next thing that we need to do now is to make these replacements, we bring them here, as simple as that. So that means that this small formula that we are talking about now becomes A 2L over A, which is like that. And when you do the maths, from there you find that what you actually get is the square root of 2AL, as simple as that. So that is it. For sure you know that this is F, which is equal to mg cosine of theta. Sorry. Right. So we continue. Okay, maybe I can even remove this. Let us look at the spring. So that is our body there. We have a spring that is hooked at a certain pivot, and then the next thing that we are having is the spring in between, then we have the body here. So, in this event, if we want to pull this body in this direction, what amount of F do we require? That is the question. So we know for sure that we are asking to say how much work is done to move the block. If we want to move it in this direction, so we'll ask ourselves to say how much work is what is done to move the block. All right. So the first thing that we want to mention is that when the body is moving in this direction, it means that F is positive, and when it is coming this way, it means that F is actually negative. So you have to put that in mind. And then how do we define the F? We know for sure that F is nothing but Kx, or the change in the X direction. Remember, every time you have a question like this, please bear in mind that you can actually put your drawing here so that you are not confused. This is your X direction, this is your Y direction, this is your origin. So the movement here is just in the X direction. So this, you can say, this is K, and of course I will define what K is, multiplied by the change in X. And this K is nothing but what you used to call the spring constant. I think you've done this in the labs. This is the spring constant, which is K. So F is given by K, change in X. This side, F is given by the negative of K, change in X, like that. As simple as that. Now, moving forward, we've asked the question here, how much work is done to move this block? This is the question we are trying to answer. So the implication here is that the work done, we know that the work done is equal to the change in the kinetic energy. Please don't confuse this K and this must be a small k, constant. That is the kinetic energy. So what does that tell us? This is the same as half. That is half F. Then we have X down there, which is the same as, this is the same as the work done is equal to half K, then X squared. Why is it X squared? Because this F is nothing but Kx. When you bring this here, this X multiplies with that, and you have X squared here. So your work done becomes half Kx squared, as simple as that. This is for a spring. All right, we'll move on. Okay. So we have some few examples in the notes that you have to, at your own time, you can go through. We even have solutions there. Just try to peruse through. I will not go through all of them, just those simple ones that I'm highlighting, which are critical for your understanding. Okay, I think we have talked much about work. Let's look at power. Okay, we look at power, I've mentioned. So, like I said, work is F multiplied by D, or the change in kinetic energy. The energy is nothing but the ability to do work, and power is the rate at which work is done. As simple as that. So let's look at this power that we need to overcome friction. What does that mean? Let's look at an example straight away. We've defined what power is, and we've said that power is nothing but the work done over the change in time. As simple as that. Now, what we want to check is, in an event where you have a block on the floor, for example, and then you want to pull it in a certain direction, which is F. If we are pulling in this direction, or we are trying to move this box in this direction, it means that there should be an opposing force which is in the opposite direction, which we are calling the friction force. Okay, and of course, this we normally denote it as F with a small letter F down there to indicate that this is not actually the actual F that we are talking about, but the F that opposes the amount of power that we are applying there in the opposite direction. Okay, now straight away we can state that in this case we see that this is our X direction, as simple as that. So straight away we can actually say that the power here is nothing but the work over change in time, over the change in time, which is nothing but F changing X, because this we know that this is the same as the work done is FD over the change in time, but this D is in the X direction, so straight away you can say F change in X over the change in T, which is the time. So you can say power is nothing but F change in X over the change in time. As simple as that. All right. So what does this entail? We see that from here, power is given by F multiplied by the change in X over change in time. What is this? By definition. By definition, we know that the change in displacement over the change in time gives you the velocity. So, in short, you can say power is nothing but F multiplied by V. As simple as that. So all those manipulations you are expected to know at this level. When you look at that, because it's not always that you will be given the V, or you'll be given the X, or you'll be given the time. So you need to make a lot of manipulations here in order to find what you don't have out of the data that you've been given. And of course, I shouldn't forget to mention something here which is important, of course. So I should be quick to actually mention the following. So we are saying the amount of F that is opposing this actual F that we are applying, which we are calling F friction, is nothing but the mu multiplied by N. This is another very important formula that you shouldn't forget about. A lot of students also forget about this formula. So please don't forget about this, and I urge you not to do that. So here, this of course, we are saying, this is the friction force that we have. This is our mu, which is the proportionality constant. So that is our constant there. and this is the normal force. As simple as that. Okay. Now, having said that, we'll push on our notes. Okay, I'll give you an example. Right. Okay, let's look at this simple example here. Okay, so if we pull this in that direction, the meaning is that we are going to have such an arrangement. We have our block which will come down here. Okay, so the distance that it would cover here, we are calling it x. So what about the work done? If, for example, this spring has a spring constant K1, this one has a spring constant K2. So how do we define the work done? So we know that if K1 and K2 are not the same, it means that we cannot easily combine them. So the simplest way is to say the work done must be equal to half. Then we have K1. In this case, first we are solving for this spring. K1, then x1 squared plus half into K2 x2 squared. As simple as that. So what does this entail? Straight away you can factorize the half from here, and what you remain with is K1. In this case, we have K1 plus K2. And of course, since x is the same, you can straight away bring the x squared outside. As simple as that. So this must not be 1 and 2, this is just x. So you can easily say that the work done here is nothing but half the spring constant 1 plus spring constant 2, then multiplied by the displacement that you've pulled this going in that direction. As simple as that. Okay, we shall end here for today, and that ends lecture 1. The next time we meet, we'll look at lecture 2. I'll try to find some time so that we can make up for the time that we missed last week, and then we can try to see how far we can go with our notes. So I'll attend to few questions before I leave. Let me just move to the other desk. So if you have any question, please just type it out, then we can discuss it. Next time we meet, we shall look at momentum and collisions. That is lecture number 2. So get to the slide, please study in advance. And where you don't understand, please find time to ask. It's very important. We are here to save you. We are here to help you attain your career. Thank you so much. Wish you well and study well, and I wish you all the best in the upcoming final exams. Bye bye for now.